The year 1949 marks a pivotal point in the history of electronics, a moment crystallized by the publication of Physical Principles of the Transistor by John Bardeen, William Shockley, and Walter Brattain. This seemingly modest paper, emanating from Bell Telephone Laboratories, encapsulated the theory underpinning a device poised to revolutionize the world, the transistor. Understanding the significance of this publication requires examining the scientific landscape that preceded it, the intellectual battleground where the concept took shape, and the seismic impact it had on subsequent technological development. Before the transistor, the vacuum tube reigned supreme. These glass enclosures, delicate and power-hungry, serve as the linchpins of electronic circuits, amplifying signals and performing logical operations. Tubes enabled radio broadcasting, long-distance telephony, and early computing. However, their limitations loomed large. They were bulky, generating significant heat, requiring substantial power supplies, and prone to failure. The search for a smaller, more efficient or reliable alternative became a driving force in electronics. The quest for a solid-state amplifier predated World War II. Early attempts focused on utilizing semiconductors, materials with electrical conductivity intermediate between conductors and insulators. Investigators noted that certain semiconductors, such as silicon and germanium, exhibited peculiar behavior when exposed to electric fields or impurities. However, a comprehensive understanding of these phenomena remained elusive. The quantum mechanical theory needed to unlock the secrets of semiconductors lay nascent, hindered by the formidable mathematical challenges inherent in modeling the behavior of electrons in complex SAW. World War II and its aftermath significantly influenced solid-state research. The pressing need for improved radar and communication systems spurred intense investigation into semiconductor materials. The development of silicon and germanium diodes for radar detection provided invaluable experience in materials processing and device fabrication. Furthermore, the theoretical foundations of solid-state physics underwent rapid advancement, spurred by the likes of Felix Bloch and others who developed band theory. These advancements provided the conceptual framework required to understand the behavior of electrons in crystalline SAW. The intellectual environment at Bell Labs proved crucial to the transistor's genesis. William Shockley, a brilliant theorist with an ambitious vision, spearheaded the semiconductor research effort. He assembled a team of talented physicists, including John Bardeen, an expert in surface physics and superconductivity, and Walter Brattain, an accomplished experimentalist with a profound understanding of materials. This synergistic combination of theoretical and experimental expertise proved essential to their success. Initially, Shockley envisioned a field effect transistor, which modulated the conductivity of a semiconductor by applying an external electric field. While this approach seemed promising in theory, attempts to realize it experimentally consistently fell short. Surface states, defects on the semiconductor surface, stubbornly screened out the applied electric field, preventing effective modulation of the material's conductivity. The project appeared blocked. Bardeen and Brattain, focusing on the perplexing surface state problem, began experimenting with germanium. They discovered that by carefully controlling the surface conditions, they could induce current amplification. Their breakthrough came in December 1947, when they created the first point contact transistor. This device consisted of two closely spaced gold contacts pressed against the surface of a germanium crystal. By injecting current through one contact, they could control the current flowing through the other, achieving amplification. The Physical Principles of the Transistor paper, published in 1949, laid out the theoretical framework for understanding the operation of this novel device. It carefully delineates the physics of minority carrier injection and transport in the germanium crystal. The paper described how applying a small forward bias to the emitter contact injected holes, minority carriers in N-type germanium, into the semiconductor. These injected holes then diffused to the collector contact, where they were extracted by a reverse bias, resulting in current amplification. The paper is notable for its careful analysis of the role of surface states. Bardeen, Shockley, and Brattain recognized that surface states played a crucial role in pinning the Fermi level at the surface, influencing the behavior of the semiconductor near the contacts. The paper describes the relationship between the surface potential and the injected carrier concentration, offering insights into optimizing device performance. While the model presented in the paper contained certain approximations, it successfully captured the essential physics of the point contact transistor. The initial impact of the transistor was significant, albeit initially contained within the scientific community. It demonstrated definitively the feasibility of solid-state amplification. This engendered immediate excitement among fellow researchers. The device's small size, low power consumption, and potential for high reliability offered a compelling alternative to the vacuum tube. However, the point contact transistor presented several limitations. It was difficult to manufacture reliably, It exhibited relatively low gain and proved sensitive to environmental conditions. Shockley, driven by his vision of a more robust and controllable transistor, continued his theoretical work. He conceived a different type of transistor, the junction transistor, which employed a layered structure consisting of alternating regions of N-type and P-type semiconductor material. In 1951, he published his seminal paper describing the theory of the p-n junction. This work established the foundation for understanding the behavior of these junctions and their role in transistor operation. Shockley's junction transistor, while initially proving frustratingly difficult to fabricate, eventually became the dominant transistor design. It offered several advantages over the point-contact transistor, including higher gain, improved reliability, and greater ease of manufacture. The development of the junction transistor marked a crucial step toward the widespread adoption of transistors in electronic circuits. The legacy of physical principles of the transistor extends far beyond the initial point-contact device. It provided the conceptual framework for understanding all bipolar transistors, including Shockley's junction transistor. The concepts of minority, carrier injection, diffusion, and recombination, elucidated in the paper, remain fundamental to the design and analysis of bipolar transistors. Furthermore, the paper stimulated intense research into semiconductor materials and device physics. Scientists and engineers worldwide began exploring new semiconductor materials, developing advanced fabrication techniques, and devising novel transistor structures. This research led to the development of the integrated circuit, also called the microchip. This creation revolutionized electronics, enabling the miniaturization and mass production of complex electronic circuits. The transistor and the integrated circuit fuels the digital revolution, transforming computing, communication, and countless other aspects of modern life. From personal computers to smartphones to the internet, nearly every aspect of our technological infrastructure relies on the principles outlined in that 1949 paper. It also transformed the nature of scientific inquiry itself, creating a powerful feedback loop between theoretical models and experimental validation. Indeed, the iterative process of model refinement, driven by experimental data, became a hallmark of modern solid-state physics. The development of the transistor also highlighted the importance of interdisciplinary collaboration. The success at Bell Labs stemmed from the confluence of expertise in physics, materials science, and engineering. This model of collaborative research, breaking down traditional disciplinary silos, became increasingly prevalent in scientific endeavor. It is also worth appreciating some darker ironies. While Shockley, Bardeen and Brattain shared the Nobel Prize in Physics in 1956 for their work, the relationship between them became strained. Shockley's management style, often characterized as autocratic and demanding, created friction within the group. He felt that his contributions received insufficient recognition, leading to resentment and ultimately to his departure from Bell Labs. This highlights the challenges of collaborative research and the complexities of human relationships, even among brilliant minds. The story of the transistor also serves as a reminder that technological innovation often arises from unexpected places. The initial focus on surface states, initially viewed as a nuisance, ultimately led to the discovery of the point-contact transistor. This underscores the importance of pursuing fundamental research, even when the immediate applications remain unclear. Serendipity often plays a role in scientific discovery, rewarding those who remain open to unexpected findings. Furthermore, the rapid pace of technological advancement underscores the importance of continuous learning and adaptation. The electronic landscape of 1949 bears little resemblance to the landscape of today. New materials, new device structures, and new circuit architectures continue to emerge, driven by the relentless pursuit of improved performance and functionality. The ability to adapt to these changes, to master new concepts and techniques, remains essential for success in the field of electronics. In conclusion, Physical Principles of the Transistor stands as a foundational document in the history of electronics. It provided the theoretical framework for understanding the operation of the transistor, a device that revolutionized the world. The paper spurred intense research into semiconductor materials and device physics, leading to the development of the integrated circuit and fueling the digital revolution. The legacy of this seemingly modest publication continues to shape our technological landscape,